since this is a lot of review material, and the time lab on Friday is going to be a question about linked lists and trees, and if I can figure out a way to do both, then I'm going to do both, like a question that would involve a linked list and a tree. So let's just go ahead and get started with this. We're sorry, Firefox says start. I don't care, Firefox. You're always a problem. Okay. So if you go into, let's see. Oh, come on. Display. 1 second, because mirror. I always line it to mirror. Well, it's you. Keep changes. Okay. So, let's see. So, let's see. Yeah, it's in classroom. So under the classroom and in your destruct folder, there should be a study guide file, right? Under the GitHub link. This is just simply a list of all the stuff that you need to that I mentioned that's important to study. Recursion really isn't implemented too much in the exam, except in relation to trees. Why? Because why have a separate question when I can test two things at once with the same question, right? Because the test is already, I have only so much room to do. So this is a list of all the stuff you should be able to expect. If I don't typically write a practice final for this, I like to instead just simply look at what other schools have. And so if you need more, you can just simply, Google data structures final exam, and you'll get similar links to what I got. So I went ahead and grabbed 4 here, which I thought were pretty good and promising. Some are more promising than others, but if you do this, typically because of the way data structures is typically taught, where you can actually split it up between a couple classes, if you happen to find stuff like that's going over big O notation that you don't really, that you don't fully understand, that's okay. Really? Come on. If you find stuff you don't particularly understand, that's okay, because you can always move. Are you kidding me? Okay, there's Firefox. There we are. I don't know why I've always had such trouble with Firefox on this computer. I'm assuming it's because of... All right, here we go. So first, let's see. I think this will be the second link that I'm going over. So this is the Computer Science E119 practice exam and I believe it's from Harvard. So there we go. Okay, so I like this one because it's multiple choice, but the questions are really good. There we go. So there's some of the other ones populating. So we'll go ahead and get started here. Again, these can be no, that's terrible. Oh, there it is. Page width. There we go. Nice and easy to read there. All right. So you can specify up to 2 answers. Oh, I like that policy, basically, where it's multiple choice, but you can guess 2, and your second choice is counted for less credit. So, okay. So let's get started. Let's get this party started, so to speak. Right? So, suppose that items A, B, C, D, and E are pushed in that order onto an initially empty stack. S is then a stack S. S is then popped 4 times. As each item is popped off, it is inserted into an initially empty queue. If 2 items are then removed from the queue, what is the next item that will be removed from the queue? If you are trying to do this problem in your head, that is bad, right? If you can draw it, then draw it. And it always makes things so much easier, right? So let's go ahead and see this one. So we've got, just making sure it's not so we've got a stack and we've got a queue. So stack, right? And then a queue, right? So here's our stack. We push A, B, C, D, E into the stack. That means that if we were to pop all the items from the stack, we'd get E, D, C, B, A, right? It'd be in reverse because of the stack. All right, so S is then popped 4 times. As each item is popped, we are going to put it into the queue. Right, that's not bad. That's not bad either at all, right? That's pretty easy, right? So we pop it from E. So we pop it. Then we pop this and NQ it. We pop C and then NQ it, and then we pop D. So B, and then we NQ it, right? Because we pop 4 times, and every item that gets popped gets NQ'd, right? Now, if 2 items are then removed from the queue, you always remove items from the front of the queue, so ED. What is the next item that's going to be removed from the queue? C, right? Whatever at the front, right? Fairly straightforward question. Just making sure you know stacks and queues. All right. Oh, okay. I was still selecting the wrong thing. All right. If the binary tree below is printed by a pre-order traversal, what will the result be? Right? Pre-order means what? It means handle myself, then handle my left child, then handle my right child. All right? So anything that starts with 9, anything that starts with 9 is patently wrong, right? Because 9's all the way at the bottom over here, 6 is at the top, so our answer has to start with 6. Right? And we also know that 6 followed by a 9 has to be wrong, because that makes no sense. We'd be skipping 17, right? Right? So pre-order, we have to handle ourselves first. So we do 6, then we handle our left child. Our left child says I'm going to handle myself first, which is 17. Then I'm going to handle my left child, which says I'm going to handle 9. So 6, 17, 9, then 4. Right? Then we'll do 22, 16, 12. Right? This answer is not right because it says I'm going to handle myself, then I'm going to handle my children, and then I'm going to go across the bottom. 6, 17, 22, 9, 4, 16, 20, 12. That's not any traversal we happen to have studied yet. That's actually a level order traversal. That's kind of a breadth first search, right? A breadth first traversal. Okay? All right, so let's go over stuff so let's go over this concept question. So a graph implementation that uses a 2-dimensional array to represent the edges would be most reasonable for which of the following cases? Now, there are 2 ways to implement graphs. What are the 2 ways to implement graphs that we've learned? Yes? Adjacency matrix and adjacency list. And they essentially, and why would you use one over the other? If it's sparse or not, right? If it's sparse or dense, right? If it's a sparse graph, we want to use an adjacency list, and if it's a dense graph, we want to use an adjacency matrix, right? So, now what do we consider a sparse graph or a dense graph? What was the cutoff point in our that was mentioned in our slides? Anybody remember? 20. Yeah, 25%, right? If it's more than 25%, if more than 25% of all possible edges exist, then we consider that a dense graph, and we use an adjacency matrix. Otherwise, we'll use an adjacency list. So here, we've got 1,000 nodes and 12. So we're asking which one of these is best to use an adjacency matrix for. Okay? So 1,000 nodes, 1,200 edges. Okay? So if I've got 1,000 nodes, how many possible edges are there? Right? You can have one edge for every single pair, right? Plus one edge between yourself, right? Right? If I've got a graph over here, right? I can have one edge between every other guy and myself for every single node. So if I've got 4 nodes, that's 4 possible edges for each node. So for a grand possible total of 16 edges, right? The maximum number of edges you can have is number of vertices squared, right? That makes sense to everybody? So if there's 1,000 nodes, then there's possibly 1,000 times 1,000 edges, which is 1,000,000, right? 1,200 is not 25% of 1,000,000. That's considerably less. So that's so that's a very sparse graph. What about 100 nodes and 4,000 edges? 100 times 100 is what? 10,000. So B seems promising because there's 10,000, because that would give us 10,000 possible edges, 40,000 possible which exist. Sorry, 4,000 of which exist. 10,000 nodes again. Sorry, 1,000 nodes again. That's a million edges. A million possible edges. 10,000 out of a million. Again, that's a very small percentage. Then 20 out of 100. That's again below 20%. So this one, 40% of the possible edges that could exist did exist. So this is the best choice for that. It is actually what we would consider a dense graph, because more than 25% of the possible edges exist. How do we know that there's, right? And that's kind of the point of the adjacency matrix, right? With the adjacency matrix, right, you have a table, A, B, C, D, dot, 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 A, B, C, D. It's a, it's a 2 by 2 array. And one edge exists for and one slot exists for every single possible combination, right? If it's a sparse graph, most of these will be nulls and therefore a waste of space and a pain and a waste of time to traverse. But if it's dense, then it's actually rather more efficient than using an adjacency list. And E is just a lie, right? So that's okay. So question 4. So let's consider we've got a binary tree constructed of nodes that look like this. So they don't bother using generics. A lot of classes don't. I like to use generics because I like teaching you about Java and the way Java works. So let's consider nodes that only have integers in them, and that will be the way it's on the exam as well. We just simply consider our nodes to have integers. So they have a left and a right. Consider the following method. Public static node mystery takes in the root. And it does this. If root.right is equal to null, we return root. Otherwise, we recursively call mystery on root.right. So I'll go back to what this does in a second, but let's see. You consult 3 supposedly tech-savvy consultants, and you get the following 3 opinions about what the method does when passed a reference to the root of a binary tree. Opinion 1 says, guy number 1 says, it returns the last node visited by in-order traversal. Opinion 2 says, it returns the last node visited by a post-order traversal. And number 3 says, it returns the last node visited by a level order traversal. Again, a level order traversal, we didn't really cover it, except we did. It's a breadth first search. It's a breadth first traversal. So in other words, it would go all the way through a graph, first iterate over the root level, then the level below that, then the level below that, then the level below that. How do you do that? You don't use recursion, you use a queue. So that's the final, that's where the 10% of problem, what I would say, like I mentioned that most of the problems can be solved with using recursion. There's only a couple of them that don't use the regular traversals. It's the level order traversal. Okay, so which of these opinion is correct regardless of the contents of the tree? 1, 2, 3, 1 and 3, 2 and 3. So for a lot of these, we need to see if there's counterexamples. So what does this one do? So what does this method do? Let's just take a look at that. If we've got a binary tree, right? Got this tree, right, that exists. If I don't have a right child, I return myself. If I have a right child, I call this method on it, which will call its method on its right child, which will call a method on its right child, which will call a method on its right child, until it gets to the point where we get to a point where there's no right child. In other words, this will follow all the way down the end until we get to this final leaf at the end, right? Or not necessarily a leaf, but where there's a guy with no child, no right child, and it will return him. It will return the rightmost item in the tree. Okay. So let's go ahead and consider each of these opinions. It returns the last node visited by an in-order traversal. An in-order traversal returns everything in the order they want. So what's special about this rightmost item? What's special about the rightmost item in a binary search tree? Anyone? What kind of defines it? Yes?
The greatest item?
It is the biggest item. Yeah, it is the biggest item in the tree. So 1 is going to be true regardless of no matter what, because if you're doing an in-order traversal, the last thing in the in-order traversal is going to be the biggest thing. So this thing is going to be the biggest thing. So this mystery in 1 is true. So we can immediately rule out B and C as possible answers. So it returns the last item in a post-order traversal. What's the last item in a post-order traversal? the root. We should fire opinion number 2. Okay. Okay. And then 3. It returns a last node visited by a level order traversal. Okay. So level order traversal, right? Now this one is a bit more forgivable, because if you're thinking of a level order traversal, you might draw yourself a perfect tree like this, right? And it will definitely return the last, and in this case, that mystery will definitely return this node. However, if instead I drew a complete tree, the last node in the level order traversal is this guy over here, but the method will return this one. So 3 doesn't always work. So 2 doesn't always work, is never true. 3 is sometimes true, but 1 is always true. So our answer is A. All right, let's see. With a poorly chosen hash function, it is possible to have a situation in which the search time in a hash table of n items goes to what time? Well, yes. You could get constant time, but not necessarily with a bad hash function, right? Constant time is what we strive for, not as bad as it can get, right? So E is kind of out. N factorial? No, that's ridiculously bad. We're not, even with a bad hash function. What happens with a bad hash function anyway? My example of a bad hash function, right, is the following, where our hash is as follows. H of x, where x is the key, is equal to 0, where everything gets hashed to index 0 of our table, meaning that everything wants to go to index 0. So after you insert the first item, there's just a collision every single time. In a chaining, that means we're just simply going to add it to the end of the linked list, and this just simply results in us having a single linked list and wasting a bunch of space. In open addressing with linear probing, this means that basically the next spot will iterate to index 1, then index 2, then index 3, right? So the first one in open addressing will take this spot, no collision. The second item will have a collision here, but take this slot. The next item will have a collision here and a collision here, but then take this spot. Then collision, 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 take this spot. Then the next item, collision, 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 take this spot. Next item, collision, 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 and so on and so forth. Where, how many collisions do we have? Equal to the number of items already in the hash table, O of n. So the search, and how long would it take to search for everything? Well, we'd start at the index 0 and go through. The worst case scenario is O of n time for a hash function, which at that point, and we want to avoid that because in that case we're just performing no better than a very poorly optimized list, and we are also wasting a lot of space to do it. Okay? So let's go ahead and consider we have a doubly linked list, right? The data, next, previous, right? This might look familiar, right? So we have n, we have p. Which of the following expressions do not refer to the third node in the list, right? So we have n and p, and we want to find which expression does not refer to this node, right? What's p.next? It's the third node. n.next.next, n.next.next, that's the third node. p.previous.next, ooh, that's p. That's probably that one. But p.next.previous.next, right, the third node as well. n.next.next.previous.next, that's the third node as well. So our answer is C, right? Okay, now this one I really like because it's similar to questions that I like to ask on our exam, the best data structure to use for a scenario. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets so that it can be quickly determined whether or not a given license plate is in the database, right? I can just look at you and instantly find out, bam, are you a crook or not, right? Are you a frequent speeder? Are you a hazardous driver? Spoiler, everybody's a hazardous driver. They just don't want to admit it. So the speed of response is very important. efficient use of memory is also important, but not as important as the speed of response. So it's more important for us to, for us to get important answers than it is to save memory. However, that means that we shouldn't, just waste memory everywhere, right? Memory just doesn't grow on trees, right? Trees use memory, they don't grow memory. Okay, so which of the following data structures would be the most appropriate for this task? A sorted linked list, a sorted array with 1,800 entries, a hash table using open addressing with 1,800 entries, a hash table using open addressing with 3,600 entries, or a hash table with open addressing with 10,000 entries. In other words, I think I'm going to go ahead and interpret this question as by entries I mean the table size is that big, as opposed to how many items are in it, because there's going to be up to 1,800 people in there. So I'm interpreting this as the maximum size of the table they want to make, right? So let's go ahead and start with a sorted linked list. A sorted linked list and searching for an item in a sorted linked list does kaput, nothing, bubkiss, okay? It does nothing, nada, zilch. Why? Because to find the middle of a sorted link, because you're going to have to iterate through it to find it, right? And on average, that item's going to be halfway through there. Okay, it's sorted. So what? To get to anywhere in the linked list, you have to have a pointer to it, right? And you only have a pointer to the head or tail. So you have to iterate to the halfway point if you want to do binary search, right? Then the middle of that, and so on and so forth. It takes a long time to do that. A sorted array, on the other hand, that's not actually too bad of a choice. That's actually the most memory efficient choice for us, right? 1,800 license plate numbers, 1,800 entries, okay? And it's sorted. So we can look, how quickly can we look that up? Well, if it's sorted, then what algorithm can we use? I just mentioned it. Anyone? What search algorithm is great for looking at sorted data? Runs in log n time. Binary search, right? Binary search. So binary search takes log n time. So this is a pretty good candidate. This is O of n. This is log of n, right? But most memory efficient. So if this question was memory was the most important thing, then this would definitely be the answer to take. But it's not. So we got to keep going. A hash table using open addressing with 1,800 entries, right? Parking lot analogy, right? If we can only fit 1,800 cars in our thing, and we need to fit 1,800 people in it, right? Then we're going to get a lot of people who want the same parking spot, right? There's not a lot of open space, so or if I'm trying to add my 1,800th entry, and there's 1,799 spots already taken, it takes a while to find that last spot. We don't want to get our hash tables to get full. Once they get full, we start getting collisions, and our collisions start going up huge amounts, and it takes a long, long time to find stuff. On the other hand, a hash table using 3,600 entries, right? That means that it is halfway full, which means that there's plenty of open space, right? Sure, we're using twice as much memory, but on average, if we look at the table that's in the slides, we're hitting like 2 collisions. That's not a figure you have to remember. But by wasting by using twice as much memory as this, we're essentially getting constant time lookup, which is pretty good. So this is constant time lookup with, wasting about O of n space. And then this would speed up our time, but it'd still be constant, but not much more. But we'd be wasting a lot more space, right? There's no real need, right? We found that basically a hash table that remains 75% of the way filled up is pretty good, right? So answer is C to this one, because, sorry, not C, B. Is it D? Answer is D, because we get constant time with 3,600. Yeah.
How do you make sure that it's only up to 1,800 license plates?
You ensure that you yell at the user if they try to add an 1,800s in first one, right? That's the only really way we can ensure compliance in that, right? But they say this is what we need. What are we going to design for, right? But otherwise, you can't really ensure that just with the data structure. You can modify it. All right, Huffman tree. A Huffman tree is constructed from a text document that contains 5 characters. The character E is the most frequent character. I is the next most frequent character. Which of the following could be a Huffman tree for this document? All right, so let's take a look. So first off, we have 1, 2, and then 3. Let's go ahead and take a look at these. So first off, 1 is not a Huffman tree. Why? Because in a Huffman tree, all the symbols need to be on leaves, right? So we can just kind of rule that straight out. So now, however, 2 and 3, those resemble Huffman trees. Now, E is the most frequent character, and then I is the next most frequent character. So which of these could possibly be the Huffman tree for that? So where are the most frequent characters located in a Huffman tree?
The bottom.
Not the bottom. The least frequent characters are located at the bottom because they have the lowest weights. And so the paths are longer to hit these, right? So the most frequent characters are located closer to the top because then it takes a shorter amount of time, right? Here, E is the most frequent character, so it takes 1 bit to get to E, whereas over here it takes 3 bits to get to E and I. So here, 2 is the most likely one, right? E, it occurs much more often than basically all these guys put together, is what this is saying. And I is the next most frequent one, but hey, it's not that frequent, right? All right. So an array of 7 integers is being sorted by the heap sort algorithm. After the initial phase of the algorithm, constructing the heap, which of the following is a possible ordering for the array? Right? So before we sort it, right, because if it was sorted, we just have to, that's pretty easy. You just look at the numbers. But this one, we're saying, okay, we've done the heapify process, which is that we've turned our array into a heap. So first off, we can rule out, now all those numbers are the same. If you can quickly check, but all the numbers are basically the same. They're just in different orders. So we can immediately rule out D, because D is a min heap. And when we do the heapify algorithm for heap sort, we want a max heap, right? Now a max heap means that the biggest item is at the root, is always at the root, and the root of each subheap. So the easiest way to do this is to kind of just draw it, maybe, if you need to, right? I always encourage drawing. So let's look at item, and then see if it's a max heap, right? And fortunately, heaps are super easy to draw, right? 85, then 78, then 45, then 51, 53, 47, and 49, right? And for it to be a max heap, the root of each heap and subheap need to be the largest item in that heap or subheap. So 85 is the largest in the heap, so that's great. 78 is the largest in its subheap, but 45 is not the largest in its subheap. So that's a bit of an issue. See that? 45 is not the biggest. So A is not. Let's take a look at B. B is 85, 49, 78. Okay, it's looking fine so far. 45, 47. Okay, that's fine so far. And now 51 and 53. So this looks perfectly fine. So I'll go with B for right now, but let's go ahead and take a look at C. C says we've got 85, then 78 and 49. 78's children are 45 and 47, but 49's children are 51 and 53, and both of 49's children are bigger than it. So that's not a max heap. Now over here, in this final one, 51, his children are 43 and 49, and 51's children are 53 and 49, and 53 is bigger than 51, so that won't work. So our answer is B. All right, let's go ahead and see what this question. Oh, I'll have to remember this for the exam exam 2 next semester as opposed to making you draw a tree. This is a much better question. All right, the binary search tree constructed below was constructed by inserting a sequence of items into an empty tree. Which of the following input sequences will not produce this tree? Right? So all of them will start with 5 because we need to put 5 at the root. Then 3 is perfectly fine for next. Then 4, right? 5, 3, 4. Put in 9, And then if you put in 12, that will go there. And then 7, that will go there. Then 8, 8, boom, boom, boom. Then 6, and then 20. That seems to work just fine. Oh, but which of these will not produce the binary tree, right? A bunch of different sequences can produce this one. Okay, so now 5, 9, 3, 7, that's perfectly fine. 6, yep, so 6, boom, 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 that already exists. So 6 goes here. Then 8 can go there. Then 4. Have we put in 3? Yes, we have. And now 12, we've put in 9, so that's fine. And 20, we've put in 12, so that's fine. Now let's look at 5. Put in 5 first, then 9, then 9, then 7, then 8, then 6, then 12, then 20, then 3 and 4. So that works too. 5, 9, 7, 8, 6, 12. Oh, I was reading the wrong one. We're on D, right? 5, 9, 7, 5, 9, 7, 3, 8, 12. So we've done 7, so 6, 4, and 20. So E's got to be the one, right? 5, 9, 3, 6, 7, right? So that's not going to build it because 6 is added before 7. So that would put the 6 over here, and that would put the 7 to the right of that. So that won't produce this tree. That sequence won't produce this tree. And how utterly frustrating that they made it the very last one, meaning you had to iterate through all the possible choices, unless, of course, you start with E. So answer 3 of the 4 questions in the space provided below. You are welcome to try all 4 problems, but make sure to clearly indicate which 3 you want to grade, right? Always a nice choice for that, making the students figure out what they're worst at. So let's see. Tree. Suppose the keys in the middle row of the standard keyboard, A, S, D, F, G, H, J, K, L, are inserted in succession into an initially empty binary search tree. Draw the tree after the sequence of insertion has been made. We've done that. This is not a hard problem. In the slightest, thankfully. All right, so let's go ahead and try this. So A, S, D, D, right? Because we're doing this in alphabetical order. A, S, D, F. F comes after A, but before S, but after D. A, S, D, F. G, C, D, E, F, G, H. So G, then H, and then J, and K, and L. How convenient, right? Right? That's alphabetical order, right? Okay. Question 2. Suppose they're inserted into a succession into an initially empty 2-3 tree. We mentioned 2-3 trees exist. We mentioned that they were a type of self-balancing tree. We didn't really go over them in detail. This is one of the things where you can go and point to it and say, aha, I don't know this, and it's certainly not going to be on the exam, so I'm just going to skip it, right? So it's important to know what you don't know, okay? Part 2, hashing. So this is, of all the questions that we've gone over so far, this is potentially going to be the most useful one because this is going to be very, very, very similar to a question we always give on the final. Okay? So which is that you are given an initial empty table of size 7 that uses open addressing. We'll be inserting items with the following keys: 15, 17, 8, 23, 3, and 5. Insert these keys into each of the following using each of the following approaches. If an overflow occurs, say so and indicate the element that causes the overflow. And by overflow, they mean collision, right? If there's a collision, show how that collision gets resolved, in other words, right? So here, we're inserting these keys, and this table is a table with 7 items in it, okay? 0, 1, 2, 3, 4, 5, 6, 7. We're inserting 6 items. Our hash table and our hash function is given given a key, we want to its index in the table is X mod 7. And we resolve any collisions with linear probing. Now this may seem esoteric and arcane, and it certainly is if it's the first time you've seen it, but it's actually not too bad. Right, so let's take a look. Okay, so let's draw our table 0, 1, 2, 3, 4, 5, 6. Okay, so we want to insert 15 first. So 15 should go, let me just put this here to remind me to switch it. So 15, what is 15 mod 7, first off?
1.
It's 1. So 15 will go into index 1. Okay, that's easy enough. 17 mod 7, what's 17 mod 7? That's 3, right? Because the closest multiple of 7 without going over is 14, and that's 3 away from it. So we're going to put it in index 3. 17 is going to go here. 8 goes where? So 8 is what? 8 mod 7 is 1. So we want to put 8 here. Oh wait, that doesn't work because this is linear probing. We can only fit one thing. This is an array. We can only fit one thing here. So what do? We use linear probing and we look for the next available spot. So we put it here. So I'm just going to kind of draw an arrow to indicate that that's how that collision happened and got resolved. Right? That makes sense. Right? So now we've got 23. So let's look at 23. What is 23 mod 7? Closest, yes, 2. Closest is 21 and 2 more than that. So it's going to go into index 2. 23 is going to go in here, but it can't. So it uses linear probing to resolve it by looking for the next available slot, which is taken. So it looks at the next available slot, so you put it over here. Make sense so far? Next, let's look at 3. 3 mod 7 goes into index 3. Or it would, but 17's already taken our spot. So, and then 23 is taking our backup, so we have to go into index. So 3 ends up going to index 5. And then finally, we're going to insert 5. Right? Now 5, on the other hand, that 5 mod 7, that goes into index 5. But we can't put it in 5, right? Because 5's already taken by 3. So collision, and that gets resolved by putting it over here. Right? And notice also, as the table got more filled up, there were more collisions. That's just what happens, especially when you don't resize it. That's not something you have to worry about with this. We're just caring about, do you understand how collisions get resolved? Okay. Now here is the other question. Same hash function, but instead of using linear probing, we're using quadratic probing. Now, remember, so linear probing, the way we view that is look at the next available slot, where the next available slot is defined as I'm looking at literally the next slot, then literally the one adjacent to that, and then the one adjacent to that. So I'm first going to look 1 away from my adjacent, from the spot next to me, then 2 away from the spot from me, then 3 away, then 4 away from the spot that I want first, that I desired. Quadratic probing says I'm going to look at 1 squared away, then 2 squared away, then 3 squared, and then 4 squared. And that does include wrapping around. Okay. So, same things. A lot of the same mathematical operations. Okay. So let's go ahead and start. 15 will go into index 1, right? 15 will go into index 1. 17 will go into index 3. Okay. 8 will also want to go into index 1, but it can't. So it uses quadratic probing to resolve this collision, right? So it looks 1 squared away, which is 1 index away. So 8 goes into 2, just like it did last time. Now 23 gets inserted. What's 23 mod 7? 2, right? 23 mod 7 gives us 2 again. So we want to put 23 here. We can't, so we look 1 squared away. Okay? But we can't go there. So now we look 2 squared away from our initial spot. So 1, 2, 3, 4. And that's where 23 will go now, with quadratic probing. Okay? 1, 2, 3, 4 away from our initial spot. Okay, now with 8, now we want to insert 3. we get a collision over here. So we just simply look for the next available slot, put 3 here, and then 5. 5's open, so 5 will take it. So there weren't as many collisions when we used quadratic probing because it spread it out a bit more. That's what happens with quadratic probing. All right, and we didn't really cover double hashing, which simply means we've got a backup hash function, essentially. So let's go ahead and take a look at now another thing that will be very similar on the exam, and possibly other exams you might have to take this semester because you go over the same stuff in every graph class because we have to. All right. So graph algorithms perform a depth first traversal of the graph shown above, starting with vertices. Oh, C, those jerks, right? We're not starting from A, we're starting from C. So select the smallest edge first when appropriate. In the space below, list the vertices in the order in which they're visited. So not the order in which we're going to pop stuff off, but the order in which literally the order in which we visit stuff, right? So not the stuff that I did on the way had it on the quiz, but in the way which we visit stuff. Now the weights here, they don't actually matter except for the purposes of breaking ties. We're not breaking ties alphabetically, we're breaking ties by the length of the edge. So we're doing a depth first search from So we're doing a depth first search from C. So that makes it at least pretty easy to figure out where we're starting with. So these markers are really bright, but they smear terribly. Okay. Okay, so let's go ahead. We're going to start with C. Okay, and now let's go ahead and start with C. Now which one comes next? We select the smallest edge to do depth first search. That would be B. Because the smallest edge was between C and B. Now we're at B, and we're doing depth first search again. We've already done C already. So let's see. Let's look at all the edges B has. It has 18, 20, 17, and 13. So the next edge is A. Okay, now we're at A, so we want to select the smallest edge. We have 13, which we've seen, and 10, which we haven't, and that's the only one. So it's by default the cheapest, so we go to D next. And then D is a dead end, right? So we back up to A. A is at a dead end, so we back up to B. We've hit 17, 13, and 5. So then we have the 20 edge and the 18 edge. The next edge we want to travel along is the 18 edge, which means that we go to F. And that's a dead end because we've already seen C and B. So we back to B, and we have one edge remaining, right, to E. And so from there, we back up to C, and so we're done. Okay, guess what the next question is going to be? Same problem, but breadth first. Okay? So in this problem, it's a bit easier and a bit less circuitous to solve because, of course, all we're trying to figure out is, right, we've got like our neighbors, right? We've got our neighbors, which is, so we have our starting point, and then we have our neighbors, B and F, right? This isn't the answer, by the way, but this is what we're going to be figuring out for the answer. So we have B and F as our neighbors. So that's, we have B, F, and E for our one-hop neighbors. And then for our two-hop neighbors, we have A and D, right? So we know that basically this is going to come before this group of 3 and then this group of 2, right? That's kind of what I'm just getting at here. So our answer is going to be, so this is not our answer. I'm just kind of using this as a way to make sure that we're not getting too, confused. So we start at C. So we need to visit all of C's neighbors first, and we're going to visit them in the order in which the edges are the cheapest. So we'll go to B, then E, then F, because of that's the order in which they're cheapest. B, E, F. C, B, E, F. That's the order in which it's cheapest to get to those. Okay, B, E, F. But when we're at B, that's how we connect to A and D. And then we visit A, and then we visit D, because because going from B, it's 13 and 17. Generally, we try to do something a bit simpler, like just break your ties by alphabetical order. It's just easier and generally less painful. But they don't want to have to create multiple graphs, right? Because the next question, of course, is suppose we want we're using Dijkstra's algorithm to find the shortest path from D to E. List in order, they become known. All the vertices, a shortest path is determined in the process of solving this problem, and the length of the shortest path to each of these vertices. Right? So we'll go back here. Okay. So we're starting at D as our starting point, right? We're trying to find the shortest path from D to E. But to do that, with Dijkstra's algorithm, we have to go through all the nodes, right? We have to find the shortest path to all the other nodes we can connect to. So, okay, let's go ahead and write our 4 data structures. We have done. That is the things that we figured out the shortest path to. That is D, because we just don't go anywhere and we're there, right? To do, that's everything else. That's A, B, C, E, and F. I'm just making sure it doesn't pull a fast one on me and have a random one out of order. Okay. Okay, and then it's easiest to create a table, right? A, B, C. We don't really have to list D because again, it doesn't really give us any useful information. E and F. D for distance over here, and then the predecessor, right? Okay. And that's and then what it also wants to know is the order in which the shortest vertex, list in order which they've become known. All short nodes with the shortest path is determined using this process, and the length of the shortest path. So how do I mark which one, the order in which these stuff will be known? Well, at least on paper, that's just simply going to be the answer in which I put down done, right? Whatever's next in done, that's the next thing I figured out the shortest path to. And then whatever is after that, that's going to be the next thing that I found out the shortest answer to. So I'm not going to worry too much about that. I'm just going to run Dijkstra's algorithm, and then I'll adjust my answer based on what they need. Okay. So D to E. So we're trying to find the shortest path from D to E. Okay. It's also kind of a hint that we can stop after D. Stop once we find the shortest path to E, but it's fine. Okay. So we need to initialize this. So D has edges from to which two nodes? A and B. Right? The shortest path to get to A is 10. The shortest path to get to B is 17. We get there from D. And then everything else we don't have an edge to, so we simply say the cost to get to it is infinity. And we get there by going through D. Okay? That's the initialization step of Dijkstra's. Now to actually go through the algorithm, to actually perform the algorithm. That was just the initialization step. It's not actually that much. I just went on a pretty long time. I just simply elaborate a lot on that part. So what we do is that we go through each of these and find which of these has the shortest distance that we have that's not already done. A's that got the shortest distance, that's the smallest distance, it's not already done. Sorry. So not already done. So we'll move A into done, and then we'll consider all the other edges that come from A. So A goes to B with a cost of 13. So A goes to B with a cost of 13 is 10 plus 13 cheaper than 17. No, it's not. That's 23. That's not cheaper, so we don't adjust anything. So let's continue on. So we've got 10, 17, infinity, infinity, infinity. We've already done 10, so 17 is the next best choice. So B. So let's consider all the extra edges from B. We already know, we've already finished our distances from A and our distances to D, so we don't have to worry about that. But we have now a distance of B to C to 5. So let's see. That's actually specifically, to get to B is how much? 17? Right? So 17 plus 5 is the cost to get to C. So 17 plus 5 is the cost to get to C now. So that'll be 22. And we get there by going through B. Then to get to F, that's a cost of 17 plus 18, which is 35. So 35 by going through, sorry, that's F. Sorry, that's F over there, my bad. 17 plus 18 is for F. That's 35 to get to F through B, and then E is that southern one, is that directly downward one, so 17 plus 20 is 37. Okay, so we've got A, we've got B, so now the cheapest one of these is C. Cost to get to C is a total of 32. So, okay, so now we're over here. It cost me 22 to get to C. So let's see if there's any cheaper routes that we've discovered. 22 plus 30 is 52, that's bigger than everything. And then 22 plus 22 is 44, that's bigger than anything, so doesn't add any additional information. So we're truly done with that. Now E and F. We're done with F now because, or sorry, F is, we figured out the shortest path through because it's got the smallest distance in there. So, and both of that just leads back to stuff we've already solved, right? So we're done with F. And then finally, we're done with E because there's no more information E would add. It's the last node. So that's the order in which we solve stuff, D, A, B, C, F, E. There's our shortest distances, and there's how we get to places. Okay. So Prim's algorithm and minimum spanning trees are stuff that we didn't go over. I instead opted to go over topological sort. So, but those stuff that you'll probably get covered in algorithms class. We don't cover Prims or Kruskal's in this class, but they're pretty straightforward. They're nice greedy out. I think one of them's a nice greedy algorithm anyway. All right. So let's see. Let's look at this tree portion now. This part of the exam deals with binary trees constructed of these nodes, which we've seen before. The following Java method uses recursion to search for a key in the binary search tree whose root is referred to parameter root. If it finds a key, it returns the sparse line. So this is just simply the search algorithm, right? It looks for the number. It looks for this date. It's looking for this number in the tree, right? This is just the standard search algorithm. It's just presented in a slightly different format. Below, rewrite the search method so that it uses iteration rather than recursion, right? Which is what I've told you never to do. Any suggestions on how to do that? I'm not going to actually write it because it would be a waste of time for this class, but if you're not going to use recursion, what do you want to use? Well, actually, search is actually pretty easy because we don't really have to do too much, right? This is actually, well, I suppose I can do it fairly quickly. Let's go and open up. So let's take a look. How would I do it using recursion? Let's just go ahead and I'm assuming I'm in the loop already. While node equals null. Oh, sorry. While the node is not equal to null, and then if I get over here, I'm going to return, let's see, what did they return instead? They returned null if it was equal to null. So if I get out of this loop, I'm going to return null. So so while the node isn't equal to no, if node dot, I think it was data, what they're using is equal to the key, what were they returning? They were returning the data. Or return, yeah, so, so it was a key with the object data, got it. Okay, so we're comparing keys, my bad. If node.key is equal to the object's key, so it was kind of using, it's basically a tree map rather than our standard binary search tree. So if node key is equal to our key, return our data. Else, if node dot key is, if key is less than node dot key, node is equal to node dot left. In other words, if it's located on our left side, we go to the left. Otherwise, we are going to go to the right side. And we'll just simply terminate if our left or right side happen to be null. Right, so it's fairly straightforward. That's why I went ahead and did it. It's fairly straightforward algorithm without recursion. Why do we do it with recursion, typically? Because I'm teaching you recursion, and if I'm teaching you recursion, then I should probably write it recursively. It helps. All right, so 10 points. I like this one. Write a Java method named mirror that takes a reference to the root node of a binary tree and creates a new tree with its own roots as the mirror image of the original tree. For example, if root is a reference to the root of the tree on the left below, then the return value for root would be a reference to the tree below on the right. Hint, much easier if you use recursion. So here we pass in 1, 2, 3, 4, 5, 6, 7, and what we see is that basically we get the complete opposite of the tree, right? 2 and 3 are swapped, 4 and 5 are swapped, and also 6 and 7 are swapped, right? So let's go ahead and figure out what does this really do, and the hint is that we use recursion. Well, it's actually fairly straightforward. Let's look at me. I'm root. What should I do? I need to swap if I'm not null, I need to swap my left child and my right child, right? And then I need to tell my children to do the same thing, right? That's really it. It's a very straightforward algorithm. So, right? So again, public, static, node. I'll just leave it out again. There's no need for it. So let's just pretend we're in the body of this already. So if root equals null, return null, right? Because if we've hit the null, if we're null, then we don't want to continue any further. We just want to stop with this algorithm. That's our base case, right? If I'm not null, then what do I want to do? I want to swap my left child and my right child. So node temp is equal to root.left. Root.left is equal to root.right. So we take the memory location of root.right and put it in root.left. And then we take root.left. And we take the memory location from temp and put it in root.left. Right, so we're swapping them. I was just testing you. And if you believe that, I have a bridge to sell you. Okay, so we swapped these, and now do let's say, so now we've done that, and let's just go ahead and say mirror root dot left. Mirror root dot right. Now these technically return something, but we don't really need what they return. Honestly, the whole thing. Oh, right. I'm making a mistake here, right? I'll finish writing this and then we'll adjust it to our mistake, right? Return root. All right, so let's go ahead and take a look at what mistake I made while doing this. It says that I want to that it takes a new tree with its own binary nodes. This actually makes it slightly simpler. Okay. So if root is equal to null, return null. Otherwise, node new left is equal to, let's see, yeah, with its own nodes. So new left is equal to root dot, let's say root dot right dot data, right? Because it says to make its own nodes, right? That makes sense to everybody? Node new right is equal to new node root dot left dot data. Okay. So we've got to still construct this thing. And now, it is actually simpler. I just use recursion. So we've got our thing. So let's go ahead and see. New left, our new left side is equal to mirror root dot right, and new right is equal to mirror root dot left, right? So I create so what's going on here? I create a new left node, which is the right node, which has the right node's data, and a new right node data, new right, which has the left node's data, and then I tell, so wait a second, I'm missing something here. What am I missing? New left dot. That is the tricky part, though, right? Because I need I need to make two children here, right? I have two children, and what's going on here is that this is just simply going to be returning. Yeah, it gets even simpler than that. Sorry. Keep it simple. New left is equal to root dot right. New right is equal to root dot left. Have I just not answered this one before in class? It's quite possible. Okay? And now return new root dot data. Well, actually, new root. Yeah, this is what it needs. New root is equal to new root dot data. I am so sorry. I like this question now. It's a bit trickier than it looked at. But we had a partially correct answer, right? Then we had to iterate through it and make a better answer. New root. New node, root dot data. And then new root dot left is equal to mirror root dot right, and new root dot right is equal to mirror on the left, which will just simply return itself, but with its children swapped. And they'll all be new nodes, right? Because what do I have to do? Let's think about this now from what this does. It says, I'm going to create a new node. That's myself, okay? Then I'm going to tell my left child to make a copy of its right child, and the right child to make its copy of its left child, right? And then to do the same to their own children, right? And then I'm going to return this new copy. So there you go. So sometimes, yes, I don't always get the answer, but hey, we went from an iterative solution to an even more correct solution. That's pretty nice. What is the runtime of the implementation of this algorithm that we just solved? What is the runtime of this? Well, for each item, we create a new node, and then we call it on its children. So this is O of n because it runs once for each of the nodes in the network. In the tree. It's fairly straightforward. So that's the end of this exam. It has a couple other stuff. Let's go ahead and why don't we go ahead and start on one of the other ones as well. since we still have some time left. This is my server. It's not. Why is it having so much trouble finding? I don't know why the school doesn't let me connecting to a VPN. Here in this exam, so first off, this exam has a lot more about big O notation than we go on about. This one from Uppsala University has a lot more of these than we typically go over. In terms of, this is more detailed than I typically go over in big O notation, right? That's a bit more mathematically rigorous, which is not the purpose of this class. So let's start from problem 2. So consider insertion sort and merge sort. For each algorithm, what is the worst case asymptotic upper bound on the running time if you know additionally that the input is sorted, the input is reversely sorted, the input is a list containing n copies of the same number. For each case and the sort in each sorting algorithm, state your answer and justify it in one sentence, which is a lot more intimidating than it sounds. Basically, it's saying, what's the worst case for insertion sort and merge sort if the list is something already sorted, reversely sorted, or a list of the same numbers? That's what it's saying. So let's go over insertion sort. Insertion sort, what's the worst case scenario if insertion sorts gets a list that's already sorted? If it's already sorted, how does insertion sort work? Right? Suppose we have, right? If we've got an algorithm, if we've got insertion sort, and we get past this list, right? 1, 2, 3, ... n to n. How's the way it's going to work? It's going to create the unsorted section, the sorted section, and the unsorted section. Then it's going to take the first thing in the unsorted section and move it into the sorted stuff. And it's going to say, oh, well, 1 and 2 are already, 2 is already sorted in respect to 1, so no need to do anything. So here's our sorted section, unsorted section. Then it'll go to 3, it says I don't need to push that down. Then it'll go to 4 and says I don't need to push that down, I don't need to swap anything. Then it'll go to 5, and it says I don't need to swap anything, and so on and so forth. Insertion sort, this is, when it gets an already sorted list, that's insertion sort best case scenario. It takes O of n time for it to handle it. What about if the list is reversely sorted? Well, if the list is reversely sorted, that's the worst case for pretty much every single sorting algorithm, insertion sort included, right? What's going to happen with insertion sort is, if we've got this, we've got 5, 4, 3, 2, 1. Well, we've got our sorted section, our unsorted section. 4 and 5 will have to swap. So we've got 4 and 5. 3 will get pushed down, we'll swap with 5, and then we'll swap with 4. So we'll get 3, 4, 5. Then 2 will swap with 5, and then swap with 4, and then swap with 3. So we'll get 2, 3, 4, 5. And then 1 will swap with 5, 4, 3, and 2. So then we'll get 1, 2, 3, 4, 5. Right? So it'll take O of n squared time. What if the input is exactly n copies of the same number? Then it's sorted. See answer to question 1. If it's exactly n copies, it's already sorted. So for each case in each sorting algorithm, so that's my answer and justifying it with a sentence. Merge sort, my answer is they're all n log n time because merge sort always runs n log n time. It doesn't care what gets inserted into it. It runs in n log n time, always. That's merge sort's guarantee, and that's why merge sort is very well liked, even though it can use extra space, right? Doesn't care if it's sorted, doesn't care if it's reversely sorted. Its best case is the same as its worst case. Merge sort just doesn't care. It is the apathetic sorting algorithm. Let's see. So let's see over here. Suppose you have a set of numbers where you over some time do a constant number of insertions and a linear number of lookups to a maximum. Maintain your set of numbers. You can choose to use either a heap or a binary search tree. So in other words, we're going to be inserting items. So don't care about the number of times we have to insert, but care about the number of times you have to do a lookup because we're going to be looking up basically once for every item we put in. Let's see. To maintain your numbers, you can do either a heap or a binary search tree. Let's go ahead. This isn't going to be relevant for the exam, so moving on. I like this question for problem 5. How much time do I have left? Oh, plenty of time. Okay, let's see. So, okay. So, suppose you have a hash table and you've inserted some elements. When you inspect it, you see that the result looks like the picture below. Being a good student, you realize this is a problem. A, what is the problem? B, an example of how this problem could happen. And C, write a better hash function. So first off, let's take a look at this hash table. Is this hashing using open addressing or chaining? I heard chaining, and that's correct. This is a hash table that uses chaining. So what's the problem with this hash table? Anyone?
A lot of collisions.
Yeah, a lot of collisions. We've got a lot of collision and a lot of empty spaces, right? We've got a lot of empty spaces, right? All right, that's okay, you know, and with a linear, especially with the chaining, there should be even less space. So there's a lot of spaces. So now let's go ahead and give let's see if we can figure out if there's a hash function that can that could give us this hash table, right? Would give us this result. Now, the reason I like this question is because it's definitely not one I think is appropriate on an exam, because this one's actually, you know, unless you're really, really, really comfortable with hash tables. So let's see. Any kind of clues? Well, let's see. 0 and 30 ended up at 0. 21, 31, and 1 ended up at 2. 2 ended up at 4. 63 and 33 ended up at 6. 15 ended up at 10. 26 and 6 ended up at 12. 38 and 8 ended up at 16. Any ideas what kind of hash function? What hash function might result in this? There's a couple different ones. Yes? Yeah. If you mod by 10. Mod by 10 and then what? Mod by 10 and multiply by 2 will result in this, right? Everything that ended with 0 ended up in 0. 1s ended up in 2s. If it ended with a 2, ended up in 4. If it ended with a 3, ended up in 6. If it ended with a 5, it ended up in 10. Right? Not a great hash function there because, right, we are missing all the odd slots. None of the odd slots get filled. That's literally wasting half the space we have. What would be a better hash function? A lot of things would be a better hash function than this. One simple one would just simply be, okay, my function is h of x is equal to x mod 20, right? Because it's a size 20 hash table. And at least then, I wouldn't be missing out on the odds. Yes, I'd still get so 0 would go from, let's see, 0 would go here, 10 would go to this would go into 10, this would go into 1, this would go into 11, this would also get into 1, which again, so you'd still get some collisions, but not nearly as many. Okay, because in effect, we only had 10 spaces to work with, and now we have a full 20 to work with. Okay. So let's see. And that's really, so those are the only, so this question, that was the kind of the questions I wanted to go over that one. I like that one, that exam for that one and some other stuff. But, let's see. So let's see. All right, so let's go ahead and start on this final one before I leave you guys. So what is the organizational property obeyed by all nodes in a binary search tree? What is the binary search tree property, in other words? You can assume that all values in the binary search tree are unique. So you can tell that the person who wrote this is probably going to be a stickler for this one, if they're bothering to ask. What makes a binary search tree a search tree? You've got, so you could, of course it's open book, so you could just simply copy it verbatim from the book. But essentially, what makes every node in the binary search tree has all the items that are less than that to the left of it, all the items that are greater than it to the right side of this, and it's recursive, right? And this property holds for its left child and its right child. That's the important part for the binary search tree, right? In other words, for every tree or subtree, it can be divided into 3 sets: the root, the left subtree, and the right subtree, with all the stuff in the left subtree being less, all the stuff in the right subtree being greater, and that the roots, and that this property holds for the roots of each of the subtrees. All right, so let's give a key of a node in a binary search tree. Let the key of a node be, just let a node be x, right? Just let a node be, containing a value be x. Please give the definition of the predecessor x. Okay, or in other words, the way I refer to it as the in-order predecessor. Okay. So what is the predecessor? What is the in-order predecessor in the tree? That's the next value. That's the value that's just smaller than me, right? That is the value in the tree that is the biggest thing. It is the biggest thing that is smaller than me, right? That's your predecessor in the tree, right? Where did we use the predecessor? In the finding the next in-order predecessor in binary search trees, when we were deleting nodes, right? So part 2, given that you're at node x and you have 2 children, how would you find your predecessor x? You don't need the predecessor of x. You don't need to write code. Just how would you do it? How do you find the biggest thing that is smaller than you? You go left once and go all the way to the right, right? This is literally another way of rewriting how do you do deletion, or the hard case for deletion. Okay? And then C is fairly straightforward, just figuring out what the successor is. Why is it sometimes better to use a red-black tree or an ABL tree? Why is it sometimes better to use a red-black tree or an ABL tree instead of a normal binary search tree? Why would you want to use those special trees, the red-black tree and the ABL trees? What are those kind of trees? Right, we didn't really go over them in class. We just mentioned they exist. What was special about them? What chapter were they located in? We were not located in the tree chapter. They were located in chapter 9, which was which chapter? They were located in the chapter on self-balancing binary search trees. So red-black trees and ABL trees are self-balancing binary search trees. So why would you want to use a self-balancing binary search tree? What's the advantage of that? It keeps it balanced. So why do you want to keep them balanced? What does that ensure if they're balanced? What's the worst case scenario for a normal binary search tree? What's the worst case runtime for a normal binary search tree? O of n, right? It turns into a bad linked list. What does a balanced binary search tree ensure? So you log of n. That's exactly it. So it ensures that. So using these ensure that it takes log of n time, although there's a bit more of a performance overhead to keep it balanced. All right, so we'll continue with the other exams on Wednesday. I will try to post these as soon as possible, and feel free to share these with people in other sections.